computer. Well, good morning, everyone, for the so manyest online webinar. Today, I'm going to talk about batteries and battery monitoring. I'm mainly focused on lead-acid batteries. Lithium is in 2 or 3 weeks. 2 weeks from now, we do lithium. So next week is monitoring of systems. So today, because I thought to do battery before systems, because it's important to know how the battery works and how to monitor it before you start with full-on system monitoring. And this is the lower end of monitoring anyway, the bare essential in my opinion, but sometimes still people don't want to put a battery monitor into a system, but it's important. So battery monitoring, and then next week system monitoring, and the week after that lithium. So because you need to know, they all sort of intermingle a bit, and even I'm also going to talk about battery bank design, batteries itself, do and don'ts with lead acid, and that also already inches onto the wiring issue as well. Bad wiring can reduce the performance of your batteries as well. So wiring, that's also coming up still. So it's always hard to choose which one to do first, but they all intermix. But here we go, the presentation. Again, as usual, all the participants will get an email from me with a recording and a copy of the presentation. There's also a feature in Professional where we can upload recordings into Victron Professional. So they're gonna try that out. It got made overnight apparently, so I haven't quite investigated it properly.
You'll be the first one, Marguerite. It's brand new.
Yeah. Ah, good. Yeah, which would be nice, because then you can also access everyone else's. Is that correct?
If everyone does it correctly, yep.
Yep. So
I'll
if
be
you
available.
Don't believe me, you want to see my colleague Johannes do the same topic, then that's also possible. Or if you want to see it in your own language, we have, or French, the French are doing stuff, Spanish salespeople are doing things in their language. So, yeah. Okay, share screen, share and show. Okay. Okay, you make me the focus speaker.
Yes, I'm just bringing that up now. My mouse has been a little bit erratic this morning, and should be done.
Yeah. So today talk about lead acid batteries. Like I said already, mainly talk about lead acid, and then monitoring in general. That also applies to lithium. There are some similarities with lithium and lead acid, but that's basically the next training with lithium. But you need to know some basics before doing that anyway, hence this training. So different type of lead acid batteries. I won't go all into all types, but globally speaking, you have for Victron systems, the first thing you want to do is you want to use deep cycle batteries. And then there's different types. So there is wet batteries. So that these are lead acid batteries where you can screw those little caps off and you see the cells and the water inside, a bit like a car battery. So they're actually wet. You top them up with water every now and then. You can maintain these quite well as well. That's one benefit of the wet battery. But they make fumes and all sort of other things, so and they can potentially leak. They make corrosion more readily than sealed batteries. So then the next best thing is sealed batteries. Of that you have two types. You have ATM batteries and you have gel batteries. ATM means absorbed glass mat. So the electrolyte is not sloshing around in the case, but it's been absorbed in a glass, a bit like a glass fiber mat inside the battery. And the glass fibers are hollow. They're the capillary tubes. So all the acid sits in that mat and can't move. And it can do things like when you charge your battery, you create gas, and then this battery can reabsorb part of that again and stuff like that. So you don't lose water out of the battery unless you do something really bad to it. But more about that later. And then the other type is gel batteries, and there the electrolyte is, they've added a gelling compound to it. So they've made basically a jello dessert, and a really horrible looking gel inside that battery made of sulfuric acid and water. So it's not nice jelly. But again, it's all one solid, sort of semi-solid gel thing. It doesn't slosh around. You can use these batteries on their side. They don't leak. They don't vent ordinarily. But if something goes wrong, they still have an emergency vent. So never can you never can assume that it will never make any gas or something. That's the wrong thing. Lead acid batteries always will make a bit of gas. So that's 12 volt or 6 volt cells, the top row. So this lot. Then we have the other lot. Those are lead acid 2 volt cells, OPZS and OPZV. So they're either wet cells or they're gel batteries, and they come in 2 volt cells. So if you make a 12 volt system out of that, you have to get 6. 6 times 2 is 12. If you make 24, you need to get 12 of them. If you need 48, you need to get 24 of these batteries. The beauty is they all connect in series, and you basically decide what battery bank you want, and then you select the capacity with that bank and then make them into a really long series string. They come in different capacities. I think they range something from the one on the screen is a 15,000, I think, 1530. Yeah, so 1500. So 15,000, sorry, amp hour battery. That one is a bit smaller, but they come from small all the way to big. So you basically decide battery bank and then get the batteries. These, although we do have some of them on our price list, we don't sell them in Australia because they be impossible to get them into the country. Best to buy these locally. They're heavy, they're big. You want proper warranties and stuff like that. And that's, we don't make batteries ourselves, although we do sell batteries. So these are our batteries. That one, sort of all batteries, but we buy these because we don't have a battery factory. So we buy a really good battery and get them branded with our name on it. But we also get some say into with the manufacturer how they are made. So they're being made according to our specifications by the battery manufacturer. Next one. Yeah, so what you don't want to do in a Victron system is always a deep cycle system. That means that the battery is used for storing your energy, and then you use the energy and then you store it again. This is very different to the battery in your car. So a start battery and a deep cycle battery are two different types of batteries. Start batteries are good at delivering a really good peak current. So you start your car, starter engine turns over and wants a lot of current straight away from the battery. And the start batteries are specially made for that. So they've got thin plates, they've got big surface inside of the battery. A lot of electrons can jump across, and therefore it can start the car really well. But you can't deep cycle them. So if you start building an off-grid system and put only car batteries in it, you're gonna probably get no more than maybe even a few months out of the batteries. They don't like being discharged far and then and recharged again. So it's so don't use car batteries in an off-grid system. The second problem we sort of see a bit people using second-hand batteries, so used batteries, like ex-Telstra. For the non-Australians, Telstra is one of our telecom companies. They every now and then sell, when they redo some of their communication setups, they replace all the batteries and then they sell ex-Telstra batteries on the market. Yeah, well, ideally these batteries are usually been in a UPS-like situation, so they've never been quite empty. So people think they're still good, but they are not super good. They come in mixed bags. You don't know the age of them, how old they are. Were they already one bank, or did they come out of many other banks? So yeah, it's in Holland we have a same saying: if you buy it cheap, you pay later. Yeah, and that's basically what happens there. Sometimes you're lucky, and sometimes you're totally not. So that's and the performance of a system goes by how well the batteries perform. If the batteries can't deliver the power, the inverter or the inverter charger can't convert it and make AC out of it. So if the batteries are not good, the inverter is no good. So it's they're that closely related. So battery perceived inverter problems are quite often caused by some issue with the batteries or with the battery cabling. That's why we have a book on wiring, for instance. Also, don't mix batteries with different shapes, models, age. So you can't just intermix different brand names. You have a big bank, one battery breaks, you put a new one in. Yeah, you can sort of do that as long as it's the same brand, but the performance of the bank will always be the worst or the oldest battery. So the battery that's the most damaged, the bad brand, the smallest, whatever the smallest denominator, that's what determines the whole entire performance of your battery bank. If you crash hot battery bank, you put one bad battery in it, that's where you've reduced your whole battery bank to that bad battery, basically. So batteries don't last forever. They are consumable, so they wear out if you use them. And that's indicated in battery spec sheets and data sheets by its cycle life. So if you look in the battery data sheet, you'll see, for instance, I've got a screenshot of ours. It says here, if you discharge your battery 80% each time you use it, so 20% left, you only get 500 cycles out of a battery. But if you are being good and you don't discharge them that far, you get 1800 cycles out of them. So you can already see that cycle life relates to how deep you discharge them. So the deeper you discharge, the shorter life they will have. They basically have a certain amount of energy and life in them. So and that's also again the case for lithium. Lithium has got much higher life cycles. So if you have a system that needs to be cycled every single day, like an off-grid system, like an ESS system, like I have, maybe in a commercial vehicle that's being used every single day, like a coffee vehicle, ambulance, all those sort of things, the batteries are consumable. So if you look at how much dollars or how much cents you pay for each cycle, if you compare lithium and lead acid, lithium, although the initial outlay is a lot more dearer, your cycle price, so the price that one cycle costs, is actually less. So that's also why more and more people are finally realizing that, yes, you need to pay more money in the beginning, but once you have lithium, you actually have a cheaper cycle price than you have when you use lead acid. So that's slowly getting into to people's mind a little bit. So life is totally related to what model you have. So this little chart here, you have AGM, gel, and gel long life. Gel long life, that's basically your two-fold cells. So you can see already really big distance, and that also relates to the price. AGM battery is cheaper than a gel battery, is cheaper again than those two-fold cells. So so the more money you pay, the more life you get out of it as well. That's another thing that relates to each other. Nothing in the world is for free, unfortunately. Then the other thing that all batteries have, and mainly so lead acid batteries have, is they have battery capacity. So I forgot actually to explain battery capacity, but I assume everyone knows this. Battery has a certain capacity. Let's say the one I've got here is a 220 amp hour battery. So 220 amps in 1 hour can come out of the battery. And that capacity is rated at a certain rating. That's the C10 or the C20 rating, which means that 220 amp hours in this case, it already says at 20-hour rate. So if I discharge this battery slowly over 20 hours, I will get 220 amp hours out of it. But if I went one too far. Just realized because I can't see my screen totally. I've put my webcam in front of it. So if you discharge the battery fast, you actually have less capacity. So you've got your capacity, and the capacity, it's a mix of two slides together. I think I've made a mistake there in my presentation. So cycle life. So what this slide is all about is the deeper you discharge the battery. So if you always go to 80% discharge, so only 20% left, you have a lot less cycles than when you discharge less deep. And this is, I think, of a lithium battery, the CREF. This is not lead acid. I just realized I must have copied or pasted somewhere because the cycles are too high. But so depth of discharge relates to your cycle life. Yeah, this is a mix of two slides. There's a mistake here, but ignore that. So this is that whole thing. So if you discharge a battery slowly, you get a lot of capacity. If you discharge it really fast, so So if you discharge it at 1C, in other words, I take 200 amps out of there in 1 hour, then I only have about 30% of battery capacity. So my 220 amp hour battery is not 220 amp hour anymore. That has gone to a third of that. So that's so that's basically, so you have your spec, right? Which is, this is the 20-hour, right? And then you have, that's the maximum. More, if you do it really slowly, you actually get more. You get 120 or more. But yeah, so that relates. So you can call this in, yeah, so you can say 10-hour, 20-hour, right? You can also say C10 or C20, or some people do it the other way around. So that's what I'm trying to explain here. So C10 is 0.1 C in this graph. So, and C20 is 0.05 C. So that's depending where the number is before or after the C, that's when you divide by 1 or not. Yeah, long story, is sort of mathematical, but yeah. So basically what they're trying to say, 20 hours, it's rated for that capacity. And if you do it faster, you have less capacity. And another thing, lithium doesn't suffer from this much at all. So with lithium, you don't have this problem, which actually gives you a bigger capacity you can work with than when you have lead acids. So the difference in between, so here I try to display it in another way. So here you've got your 100% battery and you've got your 8% battery, but this was at 5 minutes or 12 minutes, and that was in your 20 hours. So the faster you discharge, the smaller your battery becomes, basically. That's the idea. The relation between these two is the Puget component or exponent. You might have seen that when you install a battery monitor, that it says Puget exponent. So for batteries, the Puget exponent is, for lead acid batteries, it's 0.7, I think. Oh no, 1.25, sorry. So that's Puget. And for lithium, that's 1.05. So lithium suffers much less from that reduced capacity when discharging a lot than lead acid batteries do. So when you install a battery monitor for lithium, and I'll talk with lithium in that presentation anyway, then you need to change that figure. But the battery monitor needs to know that because it needs to calculate an accurate state of charge, and it needs to look at rate of discharge. So if you discharge fast, then you get less capacity. Next thing, charge efficiency. So that's basically the round trip. So you put electricity into the battery, and eventually you take electricity out again. And in between, you lose energy. So inside the battery, you get a chemical reaction that tries to put all the electricity through. So first you basically make lead sulfur. You make a battery is a box of acid with 2 plates in it, lead and lead sulfate. Oh, sorry, I'm just having a mental blank there for a sec. I haven't done the battery presentation for some time. But anyway, so sulfide goes from one to the other pole, and that's what your chemical reaction is, either discharge and recharge, it turns around. So there's chemicals doing stuff, ions moving inside the battery that create electricity, and that's how you charge and discharge. This process is not ideal, so you lose things. So with lead acid battery, you get heat coming out and you get gas coming out. So with a sealed battery, part of that gas gets recombined again. With an unsealed battery or wet cell, that gas will disappear. That's why you need to keep topping those batteries up with water. So ideally, that's water vapor that you lose. If it goes wrong, instead of water vapor, it starts doing electrolysis. So you start to get oxygen and hydrogen, and that's explosive. So that's also why lead acid batteries are potentially dangerous, far more than lithium, in my opinion. But that's yeah, a lot of people don't know that what can go wrong with lead acid batteries. A lot can go really badly wrong. So you definitely use heat and you lose gas, and that means that batteries heat up during charge, but also heat up during discharge. And that heat are your losses. So for a lead acid battery, that efficiency is 75 to 85%, depending on what model and how expensive your batteries are. For lithium, that's a lot less. So the round trip the efficiencies are a lot less. This graph here, It's a bit of a dodgy graph. I mean, they're not dodgy, like the graphics are not that great, but I've never found such a good graph at all anywhere on the internet. It sort of gives you all the different battery chemistries and then puts in how much cycles you can do, so cycles on this end, and how efficient they are. So as you see, capacitors are like batteries. They're really efficient and they can do heaps of cycles. And then you have lithium ion, lead acid is here, NiCad is here. So yeah, and in the worst case, really, you call away there, but that you don't want to use as a battery, of course. But so that's pumped hydro. That's basically pumping water uphill and then taking it out again. It's not that efficient, but you can do it many times for the pump wears out and the water generator. So and that technology will be better and better. And this graph is already, I think, at least 10 years old, I think. And the technology changes, so that they might get, and they combine things, they combine technologies to make new chemistries. So that will get better and better. Lithium will start moving that way. It's already very efficient, and the cycle life will get bigger and bigger, you hope, and etc. The size of the battery becomes important. So there's a lot of research going on at the moment with batteries in general. Yeah, I've already sort of branched on it a bit. Batteries and heat. Batteries don't like it hot. If you have your battery as an average temperature of 30 degrees Celsius, you basically have half the battery life that you have if it was at 25 or 20 degrees Celsius. So the hotter it gets, the worse your cycle life will be, and the worse the battery life will be. And that's yeah, people underestimate that as well. It just wears out from too much hot. Lithiums also have a bit of that effect, but much less than lead acid has. So if you're in the middle of the Australian desert and you have a little shed where there's a battery sitting in there because you've got a small solar panel, maybe in a mining application or an off-grid station, a farm, if you have your battery sitting there at 40, 50 degrees Celsius, that's not good for the batteries. And you might not get, AGM cycle. Yeah, you have to pick the right battery for the job. So if you go in the Australian desert, you might get even less than that if your shed gets 60 degrees Celsius. So it becomes important to keep the batteries cool. So a lot of industrial type systems there actually have air conditioning inside the enclosure where the batteries are, just to keep the batteries cold. Because sun they have plenty. It's heat they have as a byproduct. So that's so it's important to keep the batteries cool. So duct some air conditioning in it. Put them in such a way that the heat can escape in the battery bank. You want to not all bunch them up really close together, and use temperature sensors. So use if this is a BMV temperature sensor, but if your unit came with a temperature sensor, use it, especially for lead acid. Lithium, other problems, and I'll talk about it in the lithium presentation, but with lead acid, you need to, also another thing is when the batteries get hot, you need to change the charge voltage. So the hotter the battery is, the lower the voltage should be, and vice versa as well. If your battery is really cold, some of you that live in colder climates might have noticed that your car won't start if it's freezing outside, and that's all because the chemistry slows down in the battery. So to be able to charge a really cold battery, you need to go up in voltage. And that's what the temperature sensor does. It changes the charge voltage depending on battery temperature. Batteries not in use. So if you have a camper van or motorhome, you have a battery in there that's not entirely full, you don't use the motorhome for a few weeks, you actually damage the battery. Well, what will happen is the lead sulfate crystals inside the battery will become really hard, and that's what's called sulfation. So that's it's not good to store batteries away when they're not totally full, and they also discharge when they are stored. So they have a tiny amount of self-discharge. They leak electricity inside. So if you put a full battery on the shelf 2 years later or 3 years later, that battery is empty. And then it's been left discharged for a while, and then it's probably sulfated, and you can throw it away, basically. So also when your motorhome or camper van is not used, it's a really good idea to plug a charger in there. nearly all our chargers have what we call storage mode. So after the 3 charge cycles, then it goes into the 4th cycle, which is storage or reduced float. And that's especially made for keeping the battery sort of combat self-discharge, keep it nicely charged. Every week it goes through a little cycle where it stirs everything up. Because another problem you can get with lead acid batteries, because they've got water and sulfuric acid inside, they call that stratification. You get a layer of water. Water is lighter than sulfuric acid. So you get the water starting to float on top of the sulfuric acid. So they start separating, and that's also not so good. So that's why that repeated absorption, we call that. So after a week of storage, we do 1 hour or so. Sometimes you can set it, but by default it's 1 hour. It will do repeated absorption that stirs all the electrolyte up. So it mixes the water and the sulfuric acid again, and then you can go again. So we've got a really good book on how batteries work on the inside and what you should and should not do with the battery and all the science behind it, and that's written by our founder Reinhard Vader. That's the Energy Unlimited book. So that's at the end of my presentation, we've got 3 links to 3 important documents that relate to this training. And one of them is Reinhard's book, as we call it, or the Blue Book. Then this is what it looks like when things go wrong. So basically, this might have been an overcharging system. Someone didn't do the charge voltages correctly. Maybe the battery was discharged all the way. Then someone tried to recharge it, didn't work anymore because there was too much sulfation. And then instead of making charge happening, all the energy is being used to split the water up into 2 components. You create a lot of gas. So overcharging and things like this, or battery damage, and then trying to charge it will reduce in gassing and corrosion of the plates. But the gas can't go away, and there's an emergency vent that will let the gas out. Sometimes you create so much that the whole battery starts bulging. That's all not a good sign. Quite often not warranty, although people get really shocked when they see this. Question or? Oh no, I thought I heard something. It's okay. So when you have a battery warranty case, always if they have a battery monitor, look at the history in the battery monitor and see what they've been up to. How far did they discharge the battery? How often did the battery have 0 faults? What's the lowest voltage, highest voltages? This is a really good detective tool, the battery monitor. Settings, especially if you have the battery monitor with just, people don't do the Bluetooth, they can't even see it's hidden in the menu somewhere that people don't even know because they've thrown the manual away. They don't even know that you can access that, but you do it. It's a non-volatile memory. So even if the battery goes to 0 fault, it still has remembered what the battery voltages are and what the history of, how many cycles has it had. So this is your eye into the battery, what's happened to it. Another trick I want to share with you is if you wonder about whether your battery has been emergency venting, is weigh the battery. Weigh the battery, well, we have the weights in our price list, but weigh a new one, weigh the broken one, and see what the difference is. If you have a few kilos difference, that means that's water or other stuff that's leaked out of the battery. So that's a way of, and there's also a way of telling if you have a good battery or bad battery. Both might claim the 220 amp hour batteries. You weigh them and you find 10 kilos different in between brand X and brand Z. Then you know that the heavier the battery, the more capacity. So sometimes people lie or have really small print on the bottom of their data sheet. And then on the ideal conditions, then it does all of a sudden a lot of more capacity. Yeah. So let's actually look at the weight in the data sheet, and that's so a 200 amp hour C10 or 220 C20 battery should weigh about 60 odd kilos. And if you have one that only weighs 55, you know, they sort of glossing things over that might not be quite there, because the weight is the lead, and that's what the quality of the battery makes. See, I've already got half an hour. I might speed up a bit because I want to try to do it all in an hour. So most of you know this. If you have 12-volt batteries and you want a bigger voltage, you put them in series, you increase the voltage. So 2 makes 24 volt, 4 makes 48 volts. So if you parallel them, then the voltage doesn't go up, but the amp hour, so the capacity goes up. So 2 110s in parallel becomes a 12-volt, 220 amp hour battery. And then you can go series parallel. So you can connect them strings of series batteries, 24, 48 volt configurations to increase the capacity. But there's a limit to what you can do and should do. So that's why we have the 2-volt batteries. So these batteries connect in series and they come in really large capacity. So we don't really want to get beyond, this is the max. We don't really want to see 4 strings or 5 strings of that happening. Even here, you don't want to go too big because then wiring issues come at play. So this is actually, I don't know whose system this was. Craig emailed me this photo. This
it was up in Harvey Bay somewhere.
Wasn't it Fraser Island, Craig?
Fraser Island, yeah.
Yeah.
So, yeah.
This isn't. Yeah. This is not what you should do. He's got 1, 2, 3, 4, 5, 10 strings of 48 volt, all with cables, and as I'll explain later why that's an issue. This is not. Don't do this, and this is good. Yeah, so that you have the same volume, the same price probably also, because that's all not cheap. You all have to put them on top of each other. It's a crazy system there. This already looks way better. It's really nice to install, and that's what, if you need a battery bank that big, you need to go to 2-volt cells or lithium. That's another option. Or red flow batteries or something like that. So you want to have batteries that are dedicated for that sort of stuff. Problem is, if you do this, and that's also what was in the Fraser Island system, all the batteries connect to each other. This could be a single battery. This could also be strings of batteries. So here in this case, I have single batteries, but these could also be 2 in series, of course. That's the same concept. Quite often people make a mistake, and this happens. Well, this is probably number 1 wiring mistake: batteries. You have a multiple battery system. The inverter is on one side. So you have 2 cables. You want to keep short cable runs. So what do? You connect the cables to the first battery you see. Problem with that is that the trip through this battery, the current wants to find the road of the least resistance. So current comes down the line, sees a battery, wants to go straight in there because this is low potential, 0 volt, while this one is 12 volt, let's say. So current wants to go in here. A little bit of current will go here, less current here, and hardly no current there. So you'll get that the bottom battery is working all the time, and the other battery at the top is probably getting undercharged, and also because of voltage drops over all those lines, so you lose voltage. And it just sits there brand new doing nothing and probably starts to sulfate or something eventually. And that bottom one will totally blow up, will wear out in less than a year, etc., etc. And that's how bad it is with some of these systems. And these motorhomes, do-it-yourself people make these mistakes all the time. So watch out for that. And then the inverter gets the blame, which is always really good. So this, again, my favorite place, the internet, Google picture search. This was a mobile system. So they've replaced 1 battery, and then they messed around with the wirings as well. So they realized that there was something wrong. So the person that fixed this battery bank had to replace one of the batteries, and then at least they fixed the wiring after that. Yeah, theoretically, this is not a good idea, but this is probably doable in this case for a non-commercial system. This is maybe acceptable, yeah. But yeah, so this is a real life problem. It happens. How to do it correctly? So you want to go diagonally. So you want, and this is all in my wiring book. You might have or might have not seen my wiring book. I wrote a whole book on wiring, DC wiring and AC wiring, and this is in the DC wiring part. So you get diagonally. So one goes here and the other one goes all the way to the other side. So that way the trip through here for the current is the same as the trip here. Same length of distance they travel. This is the easiest way of doing things correct. So this is the easiest way. Then you can use posts, so they are common points where everything like small short bus bars or actual big bolts, something like that. In that case, make the wires all the same length. You don't want to make the mistake by making these two really short wires and those longer wires. Then you have troubles with. So you want to balance things up as much as you can. So you have to look at it and say every trip has to be exactly the same. So that means that in these systems you have longer wires. My preferred way is a nice long bus bar, and you put all the batteries in between. Can even be a shorter bus bar, but again, path. And if you connect the bus bars, same thing right there also go diagonally on your bus bars like that. So that's important. If it's a really big system, you intermix inverters and batteries and all sort of other things on the bar. But yeah, that's all in my book. So have a look at the book. This can make and break a system. Use thick enough cables, and then also so on and so on. Yeah, so again, from the internet, wrong things. Here they connected in the middle. They tried their best, but still it's not ideal. Here they connect on this side. So yeah, all the other batteries. It's actually wasteful for your batteries. It's breaking one and not using the full potential of your whole entire bank. It's stupidity. And battery is the most expensive part of a system quite often, and that's a cost that repeats all over again. It's a consumable. So a lot of the money of a system goes into the battery. So why not do a proper job? That's another common mistake. This is a photo from our blog. Do not mount inverters straight above lead acid batteries. That's a really big no-no. And you see that over and over again as soon half of the systems on our blog post do this. But this can make corrosive gases, can make explosive gases. These units got relays and switches. They can make a spark and then kaboom, things blow up. Or all the electronics get corroded in here. It's not good. So you need to, they need to be on the other side of the wall. Then, or sometimes you can put a shelf in between to actually not physically have fumes going above. So a shelf would have done the trick there, or something like that. Yeah, like I said before, keep batteries cool. If you're using a temperature sensor, find the what you think the hottest part of the battery is. So pick not the batteries you first see or the batteries where the first cable goes to. Look at the whole bank and go to the corner near the wall where the least amount of air ventilation is, the battery that you think is the hottest, because heat makes more damage than cold does. So, and that's where the temperature sensor is for. It will tell the multi to change charge voltages if the batteries get too hot. So find the hottest part and consider air conditioning and stuff like that. I already sort of mentioned bits. Well, then we go to monitoring. There are several ways to monitor a battery. The easiest way and what's the most sort of handiest way is voltage. So you connect voltmeter on the battery, you know its voltage. Then you sort of know whether the battery is full or empty. And you don't know how full, you don't know how empty, and whether it's about to go all belly up sort of thing. So you can tell when it goes bad, and you can tell that it's good. But the in between is hard to get. And given that you shouldn't really let acid not discharge below 50%, you can't tell that by just looking at the voltage. But voltage monitoring is common. So systems sometimes have a little voltmeter built in. This gives you some basic idea of what's going on. So fault monitoring, we for instance have our battery alarm panel. That is a product that measures the battery voltage, and if it's too high or too low, it makes a buzzing noise. You can set this panel. If you need some really rudimentary, cheap battery monitoring, or if you need to send an alarm signal to somewhere, let's say a computer system or something like that, this panel might be handy. It just has an LED and a buzzer. Other way would be, you can even use our smart battery sense units, which I talked about earlier already in the new products, I think, or they keep reappearing. You can even use them as a Bluetooth voltmeter. You can connect them to a battery. Like Craig has got a good one, and Craig actually advertised this solution to me. He's got several of. Craig, you want to tell the story yourself, or?
Which part, Margaret?
All your little monitors on your boat.
Oh yeah. I'll just up there. Yeah, the way you can monitor on a boat, like if you have several battery banks, you can have these on each separate bank. So, for example, the crank battery, the start battery, the house battery, the bow thruster battery, and a gen start battery. I can jump on board and on my phone I can just see what the voltage is of each battery before we even start the engines up, and also the temperature settings that they display can tell you if there's a imminent problem as well. Because if you've got generally in the bow or the keel of the boat, it's a fairly cold point, and that's where your engine room is at start. So if you have say around 25 degrees in general, especially here in Queensland, there, all of a sudden you jump on board and one battery's sitting at 35 degrees. It's also a detection that there's something wrong, maybe a bad connection or poor wiring or something's going wrong. So yeah, handy little device for the sake of a few bucks. It's not very expensive and can fault find very quickly. You can use it as a simple voltmeter.
Yeah. Yeah. Thanks, Craig. Yeah. I'll continue. I might as well put the spotlight back. Thanks. Well, I'm unmuted as well. Good. Okay. Yeah. So this is, of course, their real function is to act as a temperature sensor for an MPPT charger and soon also the Blue Power, some of the Blue Power chargers. But but also Bluetooth voltmeter or temperature sensor. Interesting. Then we have indicator leads for Blue Power chargers. They have LEDs on there, which green or amber and red. So good, middle, and bad. Really basic voltmeter. Basically, it looks at voltage, and the light will go on when depending on voltage. Okay, not that accurate, and that's basically what you can maximally get. And another problem too is with voltage is when you run a load, the voltage of a battery will drop, and then you turn the load off, and then the voltage will recover again a little bit. That's just the process of the battery. And that can take up to half an hour, also depending on battery bank size and how big the load was. So voltage is not always an accurate thing. You might think, oops, my battery is empty, but then you see that the voltage has recovered 15 minutes later or something like that. So always measure a battery that's not in use for accurate monitoring. The sort of resting voltage of a battery is about 12.6 volts. So that's if you measure a battery, that's more or less always what you measure until the battery is almost empty, and then you start seeing it drop. So low voltage disconnect is similar. It looks at voltage, so that's built into our inverter chargers or inverters. The battery monitor, smart battery protect, they all have low voltage parameters. So they look at voltage. And then if the voltage is too low, they will turn the device off. Also, a lot of your appliances in the DC system might have it, like DC fridges have it, other bits and pieces, depending on the type of equipment and how expensive it was and what its purpose is. They might already have a low voltage cutoff built in. So it looks purely at voltage. And again, and this is a screenshot from one of our inverters, we set our low voltage shutdown at 9.3 volts, which is really, really low. It's actually much lower than what you really want your battery to go. If you go to 9.3 volts, you already do a little bit of damage to your battery. So it's important, not to just rely on that low voltage. And the reason why we have such low voltage is that if you load a battery up, and especially if you have a small battery bank, the voltage will drop, like I explained earlier. And inverters run big loads. It could be starting a compressor pump or some really big loads, and the voltage will drop all the time. Then you will get all these nuisance low voltage alarms. The unit might turn off while there's no reason for it to turn off, because as soon as the load is off, the voltage will recover again. So that's why we have them that low, to not have nuisance low voltage tripping. But it's not a safe, it prevents a total discharge battery, but 9.3 volts for a 12 volt battery is not good. And again, if you need the voltages for 12 or 24 volts, you just, maybe for 24, 48 volts, you just go double or quadruple. So 10 volts is 20 volts for a 24 volt system and 40 volts for a 48 volt system. So you just times 2 or times 4. So we've actually, we recognized that our voltages are really low. So we've now introduced for our inverters, and I think I saw an inverter charger with this. It might even come to our inverters chargers as well. Or I think there's one model that does this already. Is it now looks dynamically at the voltages, because the inverter or inverter charger always knows how much current goes in or out of the battery, because we have current sensing inside our unit. So if we see that a lot of current is drawn, let's say like during here we see a lot of amps coming out of the battery, then we know that this dip is not due to that the battery is just really gone low. This dip is because we have turned a big load on. So you can actually set all of these. So you can say voltage for discharge current. So, but you need to look a bit at your spec sheet. Maybe a bit of trial and error. So by default, we do not turn it on. A small inverter will have that turned off. You need to turn it on if you want it, and then you need to read the spec sheet of your batteries a little bit, do some educated guessing, maybe fine-tune the system, run with it for a while, and then make some small changes. So that's that's the downside of it. So it might also have the non-desired effect that it's a bit trigger happy. So you need to fine-tune it properly. State of charge monitoring is way better than voltage, because now you actually, like a fuel gauge, you know how full or empty your battery is. So there's two ways of indicating state of charge, or there's multiple ways actually. So we do state of charge. You can also look at time to go, or time to go we have, and or amp hours left. That's also one way you could calculate it, but they all really come down to state of charge. State of charge, that basically indicates how much is left in the battery. So 1000% battery is full and a 0% one is empty. And then sometimes a lot in some literature and on the internet and stuff, you'll find another annotation, which is DOD, depth of discharge. That means how much you have discharged. So how much is it discharged? That's the opposite. So 0% battery would be full, and so that can cause a bit of confusion every now and then. But we, with our battery monitor, we use state of charge. So that's how is it calculated? Well, basically, something like a battery monitor like this will constantly look at current going in and out, and for that it uses a shunt. So it needs like a bit of coppery thing where the current runs in and out, sends a signal to the monitor, and then it will keep calculating how much goes in and out. So it becomes important to place this shunt in the right spot. If you have loads coming off before the shunt goes to your system, the monitor will miss that. But we've talked about it in earlier presentations already a bit as well. So current in, current out. So it keeps a running tally. So basically starts, you have to tell it up front what's the size of your battery. It doesn't know that. You need to put that in. By default, we set it to 200 amp hours. So let's say you have a 200 amp hour battery. If you take 10 out, the unit knows there's 190 left. That's the really basic calculation. And then on top of it, the battery monitor takes care of charge efficiencies, Puker's components, the synchronization every now and then, looks at how fast are you discharging. So it looks at time and discharge at the same time. So all that gives it a really accurate state of charge. So that's what the battery monitor does. So we have three types. I forgot to put one type in. That's in the next picture. Battery monitors, everyone knows it, the BMV 700 and the 710 range. 700 without Bluetooth, 710 with Bluetooth, and then it's 700 or 702, and the 2 stands for 2 inputs. You can actually see them on the shunt, so there's 2. So this is a shunt of a 700 with only 1 input. That's that orange thing there. And this is the shunt for a 702, which has 2 inputs. See? So what it can do, it can measure something extra, like a start battery, like a midpoint of a battery system, or or temperature. So there's some extra features. But the basic feature basically is determining what the state of the charge of the battery is. We also have a new one now called the Smart Shunt. Same as the battery monitor, only no display. The electronics is actually attached to the shunt. And it's Bluetooth that you use to read it out. So you always need your phone to find out what it's reading. So that's a new one. Yeah, so it keeps track of state of charge. Then we have another battery monitor. It's called the Lynx Shunt. So it's part of our Lynx DC distribution system. It's a bit like the Smart Shunt will be now the cheap version of the Lynx Shunt. The problem was with also with the battery monitor. If you use a battery monitor and a GX device like a monitoring panel, people always got confused with double dials. So that's where this one comes in really handy, but also where this Lynx Shunt comes in handy. There's no display, it has no Bluetooth, but the readout is a GX device. So with the Lynx Shunt, you always need to have a color control, a Venus, a servo. You have to have a GX device in your system. And it's part of that whole DC distribution. So you've got AC in, DC in, DC out, and the shunt sits in between that. Yeah, so batteries on one side, the loads on the other, the shunt in between. I've made a little overview here. I am missing these. I need to really actually be missing them all together from the data sheet. So power consumption and the DC voltage range. So I might get the head office to add that soon. Probably have to measure it myself and find out. But yeah, but it's available up to 48 volts systems. You can do it. So I would probably think a 56 volt maximum voltage, I would say. But the power consumption is more than the other ones. That much I know. So it's more, but how much more I don't know. Yeah, they have a relay in the back. Some do, some don't. Smart Shunt has no relay. The battery monitors do have a relay, and the Lynx has. Anyway, that's your overview. Then there's another way of calculating state of charge, and that's with the multi itself. We call that VE bus SOC, VE bus state of charge. So the multi knows how much current is going in and out. So that's what I'm trying to do with this picture. So it sees what's going in and out of the battery, and it keeps track of that. So it can calculate state of charge. It's got a CPU, and it can come up with a really good figure for state of charge. But, and I'm saying but, it will miss anything that's DC, because it only really looks what itself puts in and out of the battery. It doesn't communicate with, let's say, your DC load, with your alternator, all the other things. This is all missed. So it's a really good state of charge and inexpensive because the multi is built in, but it misses things. So if you have a big DC system, always put a battery monitor in. That's really just unnegotiable in a way. To set the battery monitor up, you go into VE Configure or into Victron Connect. You can do it with as well now. And you have to set the state of charge when bulk is finished. That's more or less always 85%. Battery capacity. So if you have a 1000 amp hour battery, you have to fill that in, because otherwise it can't calculate state of charge. And charge efficiency. So for lead acid batteries, go to 75 or 80%. And for lithium, 1 or sorry, that's 0.75. And yeah, so that's a factor, not a percentage. But that's pretty straightforward. Synchronization. The battery monitor keeps a running tally of what goes in and out, but due to measurement errors and also due to having to estimate the Pucat's thing, like the Pucat's formula, so the difference in between discharge rates is only really based on 2 battery values. So you have to put the 2 values in that correspond mostly with your battery system. But if you then accidentally have a really big load running and you didn't use that Pucat number in your formula calculation, look in the battery monitor manual. It has a lot of explanations how to do all that. But you still might be a bit off, especially if you're going really fast or really slow discharge rates. So every now and then a battery monitor needs to synchronize to stay on the ball. Synchronization happens at different times within a charge cycle. So with the BMV, the battery monitor will synchronize as soon as it sees that the current is low, and the voltage is above a certain level. As soon as it sees those two things, and that usually happens after absorption stage is finished, in other words, when the battery is 100% full, it will then, the panel might have read 90 to maybe 98%, and all of a sudden it jumps straight to 100 as soon as absorption is finished, basically. And it needs to do that to stay accurate. It will start deviating over time a little bit. So it's good practice that if you have a solar system or something, and especially in winter when you might not get a lot of sun, to at least once every 2 weeks run the generator and get your batteries to go to float. So the meter synchronizes. Also, when you install a system, after installing, charge up the batteries. All the battery charge, it's all, you start fresh, basically. Start with full set and then go from there on. The multi also has synchronization moments. It does the 100%. And handy, the multi is a charger as well, so it knows exactly when float starts. So it will then make it 100%. But it also can do a second one. It knows when bulk when bulk stops and absorption finish, and then and that's usually 85%. That's what you set into that setting. And that's more or less pretty default and standard. Then another way of monitoring the battery is looking at the midpoint. If you have two batteries in series, and these batteries might not be totally equal, they have slight differences in resistances, which almost all batteries have. Then when you charge the whole set, you can have that one, because it has a different resistance, gets a bit more voltage than the other, and eventually you get the batteries out of whack. So another way of monitoring would be look at the midpoint, and if the midpoint gets too crazy or deviates more than so many %, then you sound an alarm, because then you have something wrong with your batteries. Or you need to have a good look at your battery bank and maybe individually charge both these batteries to make them the same again. Also, when you, I forgot to mention earlier, when you make a big series parallel battery system, start with full batteries. Don't start with half empty batteries. Start with the whole bench full. Maybe individual charge all the batteries and then marry them together. And that's also really important for lithium systems as well. It's important to start with all the batteries are full. Any multiple battery systems, it's a good practice. So the midpoint monitoring, two things we can do with that. We can get a unit like a battery balancer. This is a battery balancer. It's got many different little connections. It basically connects to either side of the battery and the midpoint. As soon as it sees a deviation, it will start supplementing that. Or basically discharges the high battery with a little bit of current up to 0. It's not big, 0.2 amps or something like that. The current is not big, but that's not needed. It's just enough to combat those slight differences, to make sure it doesn't become into a big difference 2 years down the track. So this will maintain and monitor that, and it also monitors the midpoint. So it sounds an alarm, and it has an alarm relay as well that you can use to send a signal to a computer system or something else, that if the midpoint goes out, then you mean that basically there's something really wrong with your battery. So battery balancer does balancing, active balancing, to make sure that this doesn't happen. And should it happen, then there is something wrong with the battery bank, it throws an alarm. So it's well, compared to the cost of a big battery bank, this is not much addition. It's not I don't know off the top of my head what the price is, but it's not such an expensive unit. So if you have multiple batteries like this, and then again, look in my wiring book, it's all explained in there really well. Link after this training. Multiple series parallel, it's if you want to monitor the midpoint and correct the midpoints, the first thing you need to do is connect all the midpoints together. But you can't just do that with any battery bank. You can only really do that if you have bus bars. Basically really chunky bus bars, because you can't have little voltage differences. You can't have that one battery is slightly low and because of different cables. So you need to do bus bars on either end, or those post points, and then connect the midpoints properly. And only then the midpoints are connected, and then you can monitor the midpoint and use it for balancing purposes. Battery balancer can also be used, so this is 24-volt systems, can also be used for 48 volts. And then you need 3 of those monitors, one for each joint in the battery. So one here, one there. So each join, and then they, become one big monitoring thing. And then you can interconnect all these alarm signals together, and then you can choose to do, so as soon as one of them has an alarm, you will get an alarm signal, and that means something wrong in the battery bank. This should have been in that system on Fraser Island, at least, I would say. That was too crazy with too many batteries. Yeah. But the smart shunt and the BMV also monitor midpoints. So they have the 2 version, or the smart shunt has it already built in, has that second input on the shunt. So there's that second. So you can do it to monitor start battery, but you can also do it to monitor that midpoint. So if your system, or you don't care about the start battery and you have a 702 or a smart shunt, maybe consider monitoring a midpoint. So that gives you early warning sign. As soon as you get so many % difference in between the 2 batteries, it will give you an alarm. Good indicator of whether there's something wrong with your battery bank. Also, if one battery stops working towards the end of the battery lifetime, the midpoints, just before that, the midpoints will go really bad. So you have then somewhere something to check. Yeah. Temperature monitoring, like I mentioned before, if your unit comes with a temperature sensor, use it, because it will adapt its charge voltages with it. The battery monitor also has a temperature sensor. This one gets connected to that second input as well. So you need a BMV 7 something 2 at least to use this. This replaces the power cable of the BMV, so it connects like I forgot not the. Yeah, so basically same, it connects here. So you put the positive onto the positive terminal. So this actually has to go to the positive of the battery, unlike the temperature sensor of the multi can be on any terminal. But we usually choose the negative because it's safer, I suppose. But this one needs to go to the positive, and that's why it has this yellow label on there, and that's why it's blue here as well. So it's physically different than this one, which has a black heat shrink on it, and it definitely looks different. So this will monitor the temperature of the battery. You can then make an alarm. The battery monitor doesn't do much with the temperature, but can do 2 things. It can make an alarm, but it can also send the temperature into the VRM system as well for memory, if I'm correct, Kai. Yeah.
Sorry, Mike, Greg, can you say it again? It can.
The BMV does send the temperature data into the GX device.
Yep.
Yeah.
That's right.
Yeah.
And you can also connect it directly to a GX device.
Yeah, now you can.
Yeah, the ones which support that, the Venus
yeah.
GX and the Turbo GX.
Yeah. In some cases, you need this temperature sensor. It depends a bit which GX device you use.
Yes, that's right. So the BMV, yeah. There's a document. I'll post a link in the chat, which disambiguates which temperature sensor you can use with which device.
Yeah, that's a good one. Yeah, maybe I might add it to the presentation in the future. And temperature monitoring can be done with those smart dongles as well, which, not only fault, but and then you can match it to a solar charger, because solar chargers don't have temperature sensors. That's where really the whole idea behind this thing is for. It will act as a temperature sensor for your solar charger, for your regular charger soon. We expand that idea. So what to do in case of a low battery alarm? So when you have low voltage, you need to disconnect the load. So we have a special device for that called the battery protect. So this is what they look like. This is a 100 amp model, and this is a 220 amp model. And so that's the size of them. Big cooling fins. They have big MOSFETs in there that will disconnect a load once it sees a voltage too low. You can set the voltage, so you can do that with the app or with a little programming loop, depending on whether you have the Bluetooth model. The smart model is Bluetooth, the non-smart. So it's programmable, and or you can even drive it with something from it. You could even theoretically connect it to the relay of a battery monitor's got a relay as well. You can even connect that relay to this remote sensor with a remote input, and then the battery monitor can turn this one off, or a smart lithium system can turn it off. So this is it can if you have a system in a boat and you forget to turn the light off and you go away for a month and you come back and all your batteries are dead because you forgot to turn the lights off, that's a really expensive mistake, which this is, again, much cheaper than the battery bank, but saves you potentially a lot of money. Talking about boats, especially even if it's in a marina, not on a trailer under a carport or something, invest in a small solar panel just to keep your batteries charged when not in use. Should something happen to the power, if it's on a unpowered mooring or something like that, put a little solar panel in just to keep your batteries charged. It's because self-discharge happens, stuff happens. Boat is always partly live because you've got bilge pumps and other things going on that stay on in the boat quite often. So that's some hints and tips there. Or solar chargers or small solar chargers have a load output load, and that also works exactly like this battery disconnect. So for up to 15 amps or for small units, it can also disconnect the load. But you can also use that load output to feed that straight into an inverter's on-off signal. So if the load output says I'm off, it also sends it to the inverter also be off, or something else on your boat that can accept with a signal. So you can be creative with that as well. One thing about the battery protect, it is direct, it's sensitive. It will only can only run from in to out in that direction. So you can use it to turn a load off. You can also use it to turn the charger off, but then you need to connect the charger on the inside and the battery on the outside. And if you turn a load off, you do it the other way around. So it goes from in to out. That's where the current cannot run the other way, because we're using MOSFETs in here. That's up close. It can all be set up with the app, and if you don't have the app, then there's a special way of programming with a little wire loop. You connect two contacts on those green blocks and then program the unit. So preset settings, and with that unit, with the Bluetooth one, you can custom set it all the way. Other thing you can do with once the batteries get low is to start a generator. So you can use, let's say, a multi looking at voltage. You can start a generator that way, but a better way would be start a generator on state of charge. So you use the alarm relay. So a BMV comes with, if you look at the back of it, it has there it is, the alarm relay contact, and that you can feed into a generator auto start, and then you can say batteries below 50%, start the generator until the batteries recover until maybe 80 or something like that, then turn generator off again. This could be, the savior of your battery system. So that's what you do when the batteries are low, you start a generator. Another thing you can do is send an alarm to somewhere else. So it can be two ways. It can be using the relay, you go straight into some secondary monitoring system, computer system of something else or something like that. A lot of the whole entire protocol of the BMV is open source. So if you're really good with computers, you can write your own code and mess around with it directly and use the data port, the VIA Direct port, to straightly go into your computer system. So there's a lot of people that do a lot of stuff out there. The advanced stuff, the support, you have to know what you're doing. We only give limited support for the do-it-yourselfers that want to go all out in the computer world sort of thing. But there's some basic things, and there's a lot of documentation on as well. And then if you have a GX device like a color control, Venus or Serbo, you use a VIA Direct cable from the data port straight into the color control, and then the color control knows state of charge. The color control itself does not calculate state of charge. It relies on stuff connected to it that it will provide. So if you use smart batteries like BYDs or red flows, it will generate a state of charge, send it to the color control or to the GX device. Battery monitor sends it, the VE bus, so the inverter charger can send it. So different sources can send state of charge to the color control. Sometimes people think the color control has a little battery symbol, that it's so smart it knows how full the battery is, but no, not really, because you need the shunt to measure the current. So the battery monitor doesn't come with a shunt. And that's also the reason we've come out with the smart shunt. Smart shunt is really nice. You don't get confused with the double display. This is it, and you just need one. There's the VIA Direct cable straight to the color control, to the GX device, and then you have state of charge without people wondering why there's two monitors in your panel, in your system. Yeah, that's it. More information. So 3 things I recommend. One is the Victron Professional Maximizing Lead Acid Battery training. A lot of the slides from this training were straight from there, basically. So it talks all about what to do and don't with batteries and how to avoid certain mistakes. Then Reinoud's book, Energy Unlimited, talks all about battery sulfation, the battery chemistry. Yeah, if you want to know more about batteries and inverter systems, but yeah, battery-wise, it's really good book. All my knowledge comes out of that book, saves you finding things on the internet. It's available in PDF or a hard copy, so you can actually order this book as well if you would want a hard copy for yeah, winter's night by the open fire on a boring Sunday night. Yeah. And then my book, Wiring Unlimited, that talks about how to wire up battery banks, what to do with wiring. In a few weeks, we will have a training for a webinar on wiring as well, based on the book. I will go through the book. So if you have questions or remarks about the book, keep it till then. Yeah, I still need to make a second edition. I've got a lot of new stuff that could potentially go in the book, but yeah, I'm quite busy with all of these webinars at the moment. But yeah, more will be added. Anyway, that's it for today. Yeah, that's good. So have you got any? I will stop the share. Yeah.
Thank you, Marguerite.
Yeah.
Great. So there are some questions in the chat. Actually, Frank, I'll get you to ask if you don't mind. I'll just unmute you. Hopefully.
Hello, can everybody hear me?
Yes, we can hear you.
Yeah.
Okay. I just had a question. If I install a lithium battery, Victron Energy one, do I need to install an extra shunt, or does the BMS send over the information to the GX device?
No, if to be able to measure depends. If you have only a multi, then you can just do with a multi-state of charge. But if you have a DC system in the so if you're getting charge from alternators or DC chargers, or if you have non-Victron solar chargers, or if you have DC loads in the system, then you need a battery monitor. So there's 2 types. One is the battery monitor all-in-one. It comes with monitor, shunt, all-in-one box. I forgot to mention that it all comes in one box. Yeah. So it's shunt, monitor, and that connects to your GX device. Or you get a smart shunt, and that's all in one. The electronics is right there, and then the only thing you need is a via direct cable that goes from here to your GX device. And the GX device, like I said earlier, takes a state of charge reading from your multi or from the battery monitor or from something else, a smart battery, and uses that. It does not calculate it itself. It relies that something is connected to it that tells it what the state of charge of the battery is. So what sort of Victron were you thinking, lead acid or lithium?
I'm thinking lithium.
Yeah, lithium, yeah, you still need, and depending if you have, and have you got a DC system? What sort of?
No, it was just a theoretical question, because you got the BMS, who already has the intelligence in it. So I was wondering, do I still need to install a shunt?
Yes.
But maybe for future expansion, it's better to install it by default.
Yeah, we don't have a shunt built into our BMS system. Our BMS system is fairly small, but I think 2 weeks from now, the lithium one is on. Join in 2 weeks for the lithium presentation. I explain heaps more then as well. So that's, but at the moment, our BMS, although it's smart, it does not have battery monitoring built in. So that still needs to. But if you go with a different type of battery, like those BYD batteries, for instance, also lithium batteries and a whole bunch of others, Pylon Tech, and they have state of charge built in. But
Okay, thank you.
All lithium has not. Yeah.
There's a question here from Nathan, and I don't think it. Oh, the question is, what temperature sensor do you use for the link shunt? Now, I don't think there is a temperature sensor for the link shunt.
Yes, there is.
There is. All right. So which one is it?
The normal one, the multi one. So
the multi one.
Yeah.
And where does it connect to?
Inside the link shunt. I have a temperature sensor coming out of mine. I can open it.
I have to add it to my my table.
Yeah, the link shunt needs to be a bit fixed up, I think. The whole.
Yeah, of course. Yeah,
I had a quick
still
browse this morning, but there's so much other important stuff we need to do still. We have a big list of stuff that needs doing.
Also, with the link shunt, make sure, I know it's advertised that way, but some people still connect to the V bus port on the color control of the Venus. It's a V CAN connection. And they'll see it, but they won't, nothing will come up on the screen.
Oh yeah, that's not in use. Yeah.
Yeah.
Yeah. Oh no, the CAN.
No, it's it. It's on there, but they got to use the V CAN port on the CCGX.
Yeah.
It's not a V bus.
Yeah, no, it is because it is CAN.
Yeah.
Yeah.
No, it's just a common thing. I had a couple of customers just in the last 2 weeks buy them, and they started just automatically connecting to the V bus and forgetting that it's an actual V CAN system. So.
I actually forgot. I actually added the link shunt this morning to the. I have no link shunt with me. I can look at my own one. Hopefully, at this time I don't trip over the cables. I'll show my own system. I've got a really long. Can everyone still see? Oh, sorry, this way. Yeah. I open my. This is my ESS system, and I have like socks on.
Good. Hey, Marguerite, have you got it on manual focus? Because it's a bit. I hope that is sharpening up.
Sorry.
No, it's all good.
Oh, it's not working.
It was out of focus. It's fine now.
Yeah. So the link shunt is there, and I have a regular temperature sensor sitting on the. Yeah. So this is my system.
I'll add some detail to the links. I'll post the documentation, although it's not going to help you right now.
So it's a normal temperature sensor, in other words.
Yeah, I'll post the link to the link shunt document.
Yeah.
And then I'll update it to include where you connect it.
Yeah. So good.
There was another question which David asked, David Woodgrove, about BMV synchronization calibration. So when the BMV resets itself to 100%, there's some few parameters you can choose then.
Yeah.
And when to choose which one and whatever. Do you want to make a comment?
Yeah, so what it looks is, it looks at the charged voltage needs to be at above a certain voltage, and the charged current needs to be below so many percent of the manual. And I would almost say read the smart shunt manual. I made the smart shunt manual, and I actually rewrote the BMV manual partly to use it. And I don't want to boast about my own writings, but I think I've explained it better in the smart shunt manual than it was originally in the BMV manual. It was a bit double Dutch in there.
Terrific. I'll have a look.
Yeah, have a good read, and if there's still questions, just ask me. But the current from the top of my head is so many percent off. So if the current drops below so many percent of the battery capacity, it's related to the battery capacity setting.
Mm-hmm.
I can look at it
4%.
right now. But it's a good. Yeah, but
yeah. So one other thing.
Normally, default settings work quite well. The only thing, once you don't really want to change this too much, so stick with default. The only thing with a battery monitor, the first thing you want to do is put the battery capacity right, and in case you have lithium, you need to change the Pucat's value, and that are really the two essential things you always need to do. And the rest more or less works quite well by default, and yeah, just leave it be. It's because you run the risk that if you start changing all these values, and they all really tailored for lead acid. So if you have lead acid batteries, just leave them default, because people start messing around with it, and then they go overboard. They can't run too far, and then the whole monitor is off from then on. It will never register the full battery, and etc. etc. And you could have the only time when you would want to change the current setting of the charged current setting is when you have a lot of DC in your system. So you always see a certain amount of DC draw, and the current never quite drops below that because of the DC usage or something. Only then you might want to tweak the settings. But let's have a quick look at the document. Yeah, and we also don't pack the manual with a smart shunt. We now have a, I might quickly do a screen share, one sec. Square sheen, yeah. Yeah, so you can, this is the smart shunt product list, or so product page. So you have two documents now. You have the manual, but you also have the quick installation guide. So what now ships with the smart shunt is just this. And actually, one of my projects for the next few weeks or months, depending on how much I have on, is to make this also for the battery monitors. So there's no booklet anymore in the box, just a 2-page document with steps, how to connect it all, QR codes that go straight to the Victron Connect manual, straight to the actual manual tool or the GX overview. And then essential settings, what we really set the battery capacity, set functionality of auxiliary input if it's there, so that's that second input. Set the charge voltage parameter. So we really just advise this. That's what we advise for lead acid, but you might want to change that a bit, but otherwise use our default. Or but with the battery monitor, smart shunt has no voltage setting. You need to actually manually put that in. But the battery monitor does self-detect what system it's in and then will set the voltage correctly. But if you've changed the battery monitor from 12 to 24 volt system, then you need to change the voltage setting. Then for lithium, the two things, you want to set the charge efficiency at 99% and the Peugeot exponent at 105. So these are the essential settings. And then the other settings, because the software in the smart shunt and the software in the battery monitor are both completely the same. So they work with the same parameters, the same way of calculation. So then if you go to the smart shunt manual, I know of an index, that's new. It was sometimes so hard finding things, so you can actually just go through the, so it starts up with installation, commissioning, operation, interfacing, all features and settings, and this is the one you want, the till current. I'll start from here. So you can actually click on it, so you don't need to leaf through the whole manual anymore. So the manual is now only online. So capacity, charge voltage. So battery voltage must be above this voltage level to consider the battery is fully charged. So you basically take your absorption voltage. That's, or maybe the float voltage, something like that would do. So what we recommend, 13.2, so that's float basically. So you want, for lead acid, the resting voltage is 12.6, so anything above there will indicate that you're charging. So 13.2 is a good voltage, I would say. So this is the float voltage, not the absorption voltage of your charger. So here it already says it. It should be 0.2 to 0.3 volt below the float voltage of your charger. Or alternatively, use the recommended. And then discharge floor, ignore that for now. Tail current is the next one. So it looks at voltage and the current. And once both of those occur, then it goes to 100% full. So battery is considered fully charged once the charge current has dropped to less than the set tail current parameter. So by default, we say 4%. So the tail current is a parameter expressed as percentage of the battery capacity. So if you have a 200 amp hour battery and it's set at 4%, yeah, you can calculate how much amps that is. So as soon as the battery monitor sees the voltage higher than the voltage and lower than this current, then it says 100%. And that's how that works. Hope that's clear. Yeah, good.
Thanks, Marguerite. There were a few other questions. Oh, actually, this is a sort of random one, but there was a question: do we have a contact in Southeast Asia or the Philippines?
Yes, we do. Best thing is to go online and find the sales manager responsible for that. And I think it might be Carsten.
I think so too.
Yeah, so if you go to Victron Energy and then clicked on contact, you see a whole, I might go screen share again. Share screen.
Yeah.
So go to Victron Energy, click on that contact, which is window in front of. Contact here. So click on that, you get this page, and then you scroll down. Asia. Oh, that's Jan. Philippines might
It's
be.
down the bottom. Yeah, there it is. Next one down.
India, Thailand, Indonesia, Laos, Cambodia, Nepal, Philippines. Philippines was the question.
Yes.
Yeah, so then Carsten. So you just email, don't ring. It doesn't work always so good. You just send them an email and then go from there. That's the common answer always. Contact sales manager, and he knows how the local situation is better than I do. So. But we have a distributor in Philippines as well, from what I know. If you want to find a distributor, you click on where to buy, and then it will show you all the distributors in your country as well.
So there's another question, opportunity to promote your book. There's a question from Neil asking, do we have any documentation about system and equipment grounding? And that would be your Wiring
Yeah, it's in the
Unlimited book. So I'll post the link to the book.
Yeah, and there's still a bit of room for improvement there as well. It's grounding is a tricky topic sometimes, and it's very different in all the different countries. There's a lot of local different regulations. So in the book, I try to explain the basics behind things. So I can't necessarily advise on how you do it in a specific country. But the aim is basically to explain how and why you need certain things. Why would you need grounding and things like that? Yeah.
Okay, I think that's all the questions in the chat. So unless there's any others, we can. Thanks for your time, Marguerite. Thanks for the presentation.
Yeah, good.
Thank you
all
to all the
for
participants.
listening.
Yep.
Yeah, so next week is monitoring. And then on the day after is the repair training again on the first day. And I'm not sure if, is anyone from WA Solar here?
No.
No. Damien had a question about software tools. And, oh yeah, I'll stop the recording as well.